Okay, so yesterday we started talking about Newton's laws of motion, right, or Monday? And so, and we said that we just studied a little bit of history about it, and Aristotle looked at the laws of motions, Galilei looked at gravity and motion, and then Isaac Newton used Galileo's ideas to create the three basic laws of motion, and we still use those today. And Sir Isaac Newton was a very smart guy. He not only studied physics, he studied mathematics and astronomy. They're all mathematically based, so that's how he came to be interested in all three of them, because he was very interested in math, okay? Okay, and we know the story. You've heard the story of Sir Isaac Newton sitting, taking a nap underneath the apple tree. That's what we learned as children. And then an apple bopped him on the head, and he thought, but then he started thinking about gravity. We told you that essentially that's kind of a myth. He would go to his farm where he had an apple orchard, because most people had to grow their own food back then. He would look outside when he was doing his writings, and he could see the apple orchard, and he could see the apples fall from the tree, and that may have got him to thinking about gravity. Okay, so that's the extent of that. Okay, and so again, he was inspired by these apples falling from the tree, and he also found there was a relationship between gravity and the moon. You know, so the moon, and we'll talk more about this later when we talk about waves. The moon affects waves coming in and out on Earth. Waves in the ocean, affects the tides. Okay, we'll talk more about that later. And we said the first law of motion tells us that an object at rest stays at rest, and an object moving at a constant velocity will continue to move at that constant velocity unless it's acted on by an unbalanced force. Okay. And this first law is also called the law of inertia. Okay, and it's something referred to as law of inertia. And inertia is a tendency of an object to resist a change in motion. And we said this guy was probably out going the highway, slammed on his brakes. He had a big, gigantic stone in his tractor trailer here. Well, it actually looks like a storage container to me. Like this might be going to be shipped someplace else, some other country or something, since it's in a storage container. But here's a perfect example of the law of inertia. He stopped his truck really fast, but he didn't tell the stone that he was going to stop. Right, the stone didn't have any brakes. Okay, so it just went crashing through the container, cargo container. Okay, so the first law basically says that tells us that the motion will not change without a net force. So if an object stops moving or starts moving, you know there is a net force. And net force also means, we also use the word unbalanced force. Okay, so if there's a net force, the forces are unbalanced. As you know, unbalanced forces causes change in motion. Okay, and we talked about the baseball player here sliding into home and how that is affected by the law of inertia. Okay, we're not doing the simulation here. Then we talked about how we wish that we could just tell our clothes to go get in the closet, go wash yourself and get in the closet. That's just not how it works. Objects don't move on their own. An unbalanced force is required. Okay, and if you need to move a few pieces of furniture in your room, would you rather move your dress with everything in it or the dresser empty, right? We answered that question yesterday, and we said we would much prefer to move our clothes when the dresser is empty, right? Because it's a lot lighter. I've done it both ways, and it's a lot easier when you empty the drawers. And did we answer the questions yesterday? We did answer these questions, didn't we?
Yep.
Okay, we answered these questions, and we'll talk about those later.
56.
Okay, huh?
The questions end at 6.
Okay, so we answered number 5 and we answered number 6. Okay, now let's look at Newton's second law. Okay, that's what we're going to talk. That's new today. We just did a little review of what we talked about yesterday, right? Now we're on new material here. So let's look at Newton's second law, and it states that acceleration depends on both force and mass, and it supports the idea that unbalanced forces cause acceleration. Remember, acceleration is an increase in speed, a decrease in speed, could be a decrease in speed, or a change in direction, okay? And so, F equals ma, what's that all about? Well, let's look at it here. Okay, so here's Newton's second law in a graph. Look here, unbalanced forces cause acceleration. And then, so forces that cause a net force on an object are unbalanced. Okay? I think I used the example of I moved the cart yesterday. I pulled it and I pushed it, right? I'm the unbalanced force. There's a direct relationship between force and acceleration. As force increases, so I pulled and pushed the cart, but I could pull and push it faster, right? So I could accelerate, or I could decelerate, right? So as force increases, acceleration increases, and then you have mass and acceleration are inversely proportional. Listen, as mass increases, acceleration decreases. The bigger it is, acceleration decreases, okay? So let's look at what this is right here. Force equals mass times acceleration. Okay, that's that mathematical formula. We'll look at that a little more here. So the unbalanced force causes acceleration. So unbalanced forces cause an increase in speed, a decrease in speed, or a change in direction. So the second law relates force, mass, and acceleration. So force equals mass times acceleration. That's a pretty simple mathematical formula, isn't it? Right? You might want to highlight that. Highlight that in there. When we do a little quiz here shortly, a reading check,
Wait, what?
you may be able to just highlight, use your highlighting tool and highlight force equals mass times acceleration. Just highlight that so that you'll know that's kind of an important point, right? It's a very simple mathematical equation, really.
Highlight what?
This right here, force equals mass times acceleration. Just highlight that right in there. Okay, so that you'll know that that's kind of an important concept to understand with this second law of motion.
Where is that at?
Should be slide 22, I think.
Oh.
There you are. Okay. Need to that music. The music's not cool, you can't hear me.
Oh, no, I got this one.
Huh?
I got that one.
Okay. Are we there? Okay, everybody got that highlighted? I'm gonna move on here. Okay, so look right here. So if you know these, look here. So we've got three different formulas here. So force equals mass times acceleration. Now, if you know force and mass, you can get the acceleration. Okay, so because acceleration equals force, what does this mean here? Divided by, right? A fraction is a division. A fraction is a division problem. You understand that concept, right?
Mm-hmm.
So if you know the force and acceleration, you can get the mass. Okay, so if you know the mass and acceleration, you get the force. So you might want to highlight all three of those. So we can arrange this to solve for the other variables. You do not need to know how to arrange it, but you do have to be able to select the right formula for solving your problem. Okay, so because we're going to do some problems here in a minute, highlight those and you'll be able to go back and say, oh, we're trying to find acceleration, so that means it's force divided by mass, right? Okay. Highlight that if you've got a piece of scratch paper, you might wanna write that on the scratch paper. I'll give you a second to do that.
Do what?
Write those three formulas down, cause we're gonna use them here in a minute.
Can you put them like on the side, like right here on
You
the?
could, yeah, you could do that.
So
yeah.
one is the right,
Or you could put it on a sheet of paper too. Okay. You'll get used to it here. You'll get the idea here in a second.
so we write F equals what?
I'd highlight those, and then if you have a sheet of paper, you wanna highlight those so you'll know they're there. And this is, slide 23 for you at home. If you're gonna do this, you can pause the video, go back to slide 23, look at the formulas, and, you'll be able to do the problems. Okay, you'll be able to solve the, acceleration, you'll be able to solve mass, you'll be able to solve force with these three, and they're simple equations. Okay, it's two division problems and one, multiplication problem to get all three of those. Does this make sense? Okay, I'm gonna move on here then. Okay, so let's look at how we can apply Newton's second law. Okay, so the second law states that if the forces increase, acceleration is gonna also increase, okay? Perfect point, look. Okay, so as I go, I get faster, right, and I'm accelerating. I'm increasing my force. I'm increasing my force, so I accelerated faster, right? Okay, so if you want to shoot a very fast penalty kick into the soccer net, how do you kick it? Very fast, right? With a lot of force. Okay, with a lot of force. Okay. Okay, so let's look right here. Anybody got a little sister or brother at home that has a wagon? Or have you ever had a wagon of your own?
I've been on.
Those are kind of nostalgic just to see one, right?
My wagon broken.
Okay, so, listen. So the second law also tells us the greater the mass, the less the acceleration, if the force is constant. Okay? So here's an example of that right here. Have you ever pulled your friends in a wagon? Well, how hard is it to pull one person in the wagon?
It depends the size.
Huh?
It
Depends on the person, you're right, exactly. How about if you add one? Is it gonna be easier or is it gonna be harder?
Harder to pull up.
It's gonna be more difficult to pull, when you start adding weight to it, right? Okay, so that's what we're talking about here. But once you get that mass to going, can you accelerate it? Oh, you can get it going pretty fast, right? But it takes more force. Okay, so as the mass increases, the less acceleration. If the force is constant, you have to add more force to accelerate more, okay? Everybody got that? Here's our first question. This is number 7. We're gonna take a grade on this, by the way. For you at home, if you need to stop the video and go back and look at the material, you can, okay? Okay, so here we are. When the force acting on an object increases, the resulting acceleration, will it increase or decrease? You can't choose remain constant. When the force acting on an object increases, what's gonna happen to the acceleration? Is it gonna increase or decrease? Mark your answer, B or C. Everybody got an answer? B or C, mark your answer, can't choose A. Okay, look right here. When an object's mass increases, but the applied force stays the same, if the object's mass increases, we just talked about that just a minute ago, you put that second person in the wagon, so the mass is gonna increase, but the applied force stays the same, what's it gonna be? Is it gonna increase or decrease? Let's go back here and look at this. What is it? The second law tells us the greater the mass, the less the what? Acceleration. So that means, does it mean decrease or increase? Mark your answer, A, B or C.
Not
Mark your answer. Everybody got an answer? Okay. Okay, so let's look right here. So when an object's mass increases, but the force stays the same, the resulting acceleration will what? Remain constant, increase, or decrease? You're on your own on this one. When an object's mass increases, but the applied force stays the same, the resulting acceleration will what? Remain constant, increase, or decrease? Got an answer? You can go back and look. I'm not in any big hurry if you want to look. Go back and look at that. If the mass increases, but the force stays the same, is it going to remain constant, increase, or decrease? Okay. I'll just tell you this, you can't choose B, A or D. Mark your answer. Don't choose B, A or D, or A or C, I'm sorry. Mark your answer, A or C, I can't choose B. Okay, here we go. Oh, here we go. Here we go. Are we ready?
I hate how I can't scroll when I have a text box. I can't scroll, I have to like have.
Okay, so, I'm gonna help you with this first problem. Okay, I'm gonna help you with this first problem. Do you guys have a calculator there that you can pull up? Huh?
I mean, we can go to the app calculator.
Would it be easier to use this calculator, or would it be easier to use one on the computer? Use one on the computer then.
Is that on here?
What?
I know the answer, though.
Is that on here?
I know the answer.
Here, let's just do it on this calculator right here. Okay, so, I'm gonna help you out with the first one here. I'm gonna set the problem up for you. Who else wants a physical calculator? No. I think I better give you one. You can choose if you wanna use the, here's our formula right here. Mass, this is the one I'm gonna help you on.
Let me use one of these.
I'm gonna set your problem up. So what's the mass? We're looking for the mass, right? So the mass equals, what's the force? 30, right? 30 newtons? Right? And then the, acceleration is 0.4 meters per second squared. Okay, so what's the total mass of the bicycle? And remember, mass is measured in grams and kilograms, right? In kilograms. Okay, so take your 30, divide it by 4, and then you mark your answer. Don't blurt out an answer. 0.4, be sure to do 0.4. Now, don't do 30 times 4. 30 times 0.4. And then you mark your answer. Don't blurt out an answer.
What?
30 divided by 0.4, I'm sorry. 30 divided by 0.4. Okay. Mark your answer, A, B, or C, and I'm gonna move on here. Everybody got that, everybody got an answer? That should be a simple one. See, these are very simple mathematical formulas. Okay, now, I'll be honest with you, and for you at home, the answer doesn't really matter so much as you know how to do the problem, right? Because the answer is always gonna be different, because the problem's gonna always be different. The key is learning the formula, okay? Mass equals, for this particular right here, we're looking for the total mass of the bicycle in U. So that would be, mass equals force divided by acceleration, okay? Everybody got an answer? I'm moving on. Okay, so let's look right here. Okay, so you're pushing a shopping cart so that it accelerates at 0.2 meters per second. That's not very fast. Do you need to change how you push on the cart for it to maintain the same acceleration? If so, in which way? If you want to, do you need to change how you push if you want to maintain the same acceleration? No, yes, or yes? Yes, push harder, yes, push softer. If you wanted to maintain the same acceleration, so what do? Do you push, do you need to change how you push it if you want it to maintain the same acceleration? That should be an easy one right there. If you wanna continue to do 0.2 meters per second, should you change anything? Mark your answer. Okay, everybody got an answer?
Wait, so you
That's an
wanna
easy
keep-
one, huh?
Wait, so you wanna keep pushing the,
If you want to maintain your speed, your acceleration is 0.2.
It looks like it's the last one.
Well, you mark your answer, A, B, or C. Think about what we just said. If you wanna maintain the same acceleration, should you push harder, should you push softer, or should you not do anything different? If you wanna maintain this 0.2 meters per second. You're pushing already and you're going 0.2. You wanna stay going 0.2. Do you do anything different? Mark your answer. Everybody got an answer?
yeah,
Okay. Okay, so what number was that? Number 10? We're gonna stop right there. And we will continue with another idea tomorrow.